Welcome to this video. In this video I am going to talk about an important concept which is called strong duality. So throughout the previous videos we have seen the primal problem and the dual problem, and we have seen that the optimal values of primal and dual problem, we take them to be equal, and there is a certain criteria under which this equality holds, which is called Slater theorem, and we will see that in detail in this video. So just to remind us, we start with a primal feasible set that I have shown here, which is the set A, and it is a set of all vectors which belongs to a closed convex cone K, such that phi of x is equal to B, where phi is a linear map from the space V to a space W, and we have a dual feasible set. A is primal feasible set, B is dual feasible set, where phi star y minus a belongs to the dual cone. So we have seen the definition of the dual cone also. So given this, we have the optimal values alpha and beta, which are primal and dual optimal values respectively, and one is denoted by supremum, over x belonging to a, and another by infimum over y belonging to b. And weak duality is nothing but alpha is less than equal to beta. So this is weak duality, and strong duality will be discussed in this video. So one of the important concepts to discuss strong duality is the idea of relative interior of a convex set. So here I have talked about that relative interior of a convex set. So it is set of all vectors in the convex set, such that for every other element that you take in the set, there exists an epsilon such that this particular combination belongs to the set. So what this means is that if you take an x, for example, in the figure, then for every y, so you pick a y, you can parameterize this line, which is itself a convex set. You can parameterize this line, and any point that you take that goes beyond this x, that point should be contained within the set. So you can take some other point y prime here, and you can also take some other point here, and this will be the convex combination of this form. And what this means intuitively is that points excluding the boundary of K are contained in the relative interior. So if I take a point in the boundary, then I can find a y such that for a little bit of epsilon I will spill over. So that is the main idea of relative interior. Now what is Slater's theorem? So Slater's theorem, as I have written here, it gives us the conditions of strong duality. So it says that if my set B is non-empty and there exists a x in the relative interior of the closed convex cone such that phi of x is equal to B, then alpha is equal to beta. So this means that if you have your B set to be non-empty, which is your primal, which is your dual feasible set, and you have your A set to be non-empty, and in turn there is something in the relative interior, this is a stronger condition, then alpha is equal to beta. Similarly, if you have the other statement is that, which is also equivalent, is that if you have your A set to be non-empty, which is the primal feasible set, and there exists a y in the output space such that phi star y minus a belongs to relative interior of the dual cone. So in these two criteria, alpha is equal to beta. So you see the criteria to satisfy alpha and beta to be equal is very weak. It is just that your sets must be non-empty and there must be something inside the relative interior of the set. So let's look at the proof of the theorem now. So this is the proof of the theorem. So we just show that 1 implies alpha equal to beta. So for that we also assume that the vector space V is span of the cone and vector space W is in the image of the linear map. So it's like this W is just kind of the image of phi. So there is not more elements than that. So this is without loss of generality, And I am going to follow here the lecture notes by John Watrous. And the idea is we consider a space of this form. So we have a space of this form. So this is W direct sum V direct sum R. So this is kind of a tuple that has three contributions, one from W, one from V, and one from R. And we define two disjoint sets. One set is called C and another is called D. So the C set is defined in a particular fashion: B minus phi of x, Z and Ax, such that Z belongs to V, X belongs to V, and X minus Z belongs to K. We will see why this definition makes sense. And set D is defined in such a way that it is 0, 0 in both the arguments. These are 0 vectors in W and 0 vector in V. And eta is a positive, not a positive, it is a number which is just greater than the primal optimal value. So this is the primal optimal value, and eta is greater than this. So this is important because this is what makes the sets disjoint. So the point is the sets are convex, which can be seen by just the idea that this phi is a linear map. If you use the linearity of the inner product and the linearity of this map phi, you can see that set C is convex. Similarly, set D is convex because this is just a number. And so the intersection of the set C and D is empty set. So this is because if this is not the case, then there will exist a x belonging to K such that phi of x is B, so that the first term is 0. So this term will be 0 if C and D have a common element. And then the last term will be equal to eta. The last term will be equal to eta. This means that the supremum value will be eta instead of alpha. So alpha will be equal to eta, but this will contradict the definition of eta, which is by definition greater than alpha. So that's a bit of bookkeeping that one needs to do here. But otherwise, it's easy to see that these two sets are convex and disjoint, so they can be separated by a hyperplane. And by separating hyperplane theorem, there exists a non-zero vector, and that vector I have shown by y, mu, and lambda, such that if you take any vector in C and take the inner product with y, mu, lambda, this is always less than equal to the same vector times any vector in D. So this is the argument of separating hyperplane theorem, and the important point is that this should be a non-zero vector. And with this idea, we can expand this particular inequality. We can expand this inequality by putting the form of C vector and the form of D vector, and this will give us something that I have shown here in this yellow star. So this is the inequality. And now using this inequality, we will consider various cases, and these cases will give us certain restrictions, which will in turn help us determine alpha is indeed equal to beta. So the first case is consider x equal to z equal to 0. So here my x vector, this is 0, my z vector is 0. I can choose them to be 0 because in principle there is no restriction in the choice of x and z, apart from the fact that x minus z should be an element of a cone, but any cone always contains the 0 element, so this is fine. So consider this particular case, and then if you put z equal to 0 and x is equal to 0, then y beta is always less than equal to lambda times eta. Here phi of 0 is 0 because the map is linear. Now here one thing is important to see is that I can always scale my inequality by mod of lambda. So I can always divide my inequality on both sides by the magnitude of lambda. So I can, without loss of generality, say that my lambda can take three values. One is -1, one is 0, or 1. So it will be one of these three values, and the restrictions that we will see will help us determine which value it is actually. So here, if lambda is equal to -1, then what I can do is I can take eta to be infinity, such that what happens is that my left hand side, this is my LHS, my left hand side is a finite value, it is a fixed value. I keep this value fixed, but I change the right hand side in such a way that I achieve minus infinity. So this is a pathological condition which is not possible. So lambda cannot be equal to -1. So lambda has to be equal to 0 or 1. Now we will see further restrictions that says that lambda will also not be equal to 0. So in case 2 now, we consider x belongs to the primal feasible set. This means phi of x is b and x belongs to the convex cone k, and z belongs to minus k. So minus k is kind of taking the negative of the convex cone, which is again a cone. It will give you a kind of every element of the cone will be multiplied by a minus sign. Then x minus z is again an element of k. So this is important, that if you have two elements of a cone, then the sum of them is also an element of the cone. This is easy to see, because if you have two elements of a cone, of a convex cone, you can take a linear combination which is a convex combination like this, where this is one element and this is another element, and then you can tune the parameter lambda 1 and lambda 2 so that it becomes x plus y. So with this x and z, we will now proceed to see what the inequality becomes. So the inequality gives us this double star. So we had the star inequality here, and from this inequality we are going to the double star inequality. And in this inequality, what you can see is that if my mu vector, which is this is also u or mu, at this point it does not matter, but the point is this u vector, if it does not belongs to the dual cone, then there will exist a vector v such that this condition holds. This is just from the definition of a vector not belonging to the dual cone. So if this holds, then I can take this vector v and scale it by a parameter, a new parameter lambda tilde, let's call it, and then I can define my z to be minus lambda tilde v, and this will belong to minus k because v belongs to convex cone k. So what this means is that now my z will be such that I can drive this inner product on the left hand side to infinity, keeping my right hand side to be fixed. So the idea is eta minus inner product ax, it has already a lower bound which is eta minus alpha, and because the sets are non-empty as a criteria of this Slater theorem, eta minus alpha is a finite value, but I can drive the LHS such a way that it becomes infinite just by choosing z to be minus lambda times v for a v that satisfies this. So this is again a pathology condition. Then this means that my u must belong to the k star. So until now what we have seen is u or this mu, this belongs to k star, and lambda has to belong to 0 and 1. Now we will rule out that lambda is 0. So to rule out this, what we will do is we will take lambda to be 0 and arrive at a contradiction. So take lambda to be 0 and x belonging to intersection of the primal feasible set with relative interior of k. I can take such a x, and further take x and z to be same. So if you do this, if you do this, you see that here lambda is 0. So inequality, in this inequality lambda is 0, so this side becomes 0. So this is upper bounding this inner product where x is equal to z. So basically u times x, this inner product, is less than equal to 0. But this is again a contradiction because x is an element of k and u is an element of k star. So ux can only be equal to 0. So by contradiction I mean if it cannot be greater than 0. So in that sense I use the word contradiction. So u times x is equal to 0, So this is a finding that we will use again. So now we shift our focus to a vector v and an epsilon greater than 0 such that this vector belongs to k. So this is just the fact that x belongs to relative interior of k. So if x belongs to relative interior of k, then x plus this vector belongs to k, because this vector is kind of like how much you add to x so that the final thing lies within k. And with this idea, we take this particular combination, and now I define this to be minus z. So once I define this to be minus z, now u times z is less than equal to 0. This we know because lambda is 0. So this is because lambda is equal to 0. And this implies I can put the z from here to get this particular side of the inequality. And u inner product x is 0. So this in turn means u inner product v is less than equal to 0 for all v belonging to k. But this in turn means that u is equal to 0. This is because u is already an element of k star. And so this by definition of k star, so k star has all the elements u such that inner product u with v is greater than equal to 0 for all v belonging to k. So with this we have lambda is equal to 0, u equal to 0. And now what we can see is that for any vector x belonging to v, then this inner product y times b minus phi of x, so this is now the inequality. So this is the inequality. This inner product is less than equal to 0. Now we know that w is image of phi. This is the assumption that we took without loss of generality. So x can be chosen such that, so phi of x we can choose it to be 2 times b, or we can choose it to be 0. And this gives us these two constraints, which in turn says that yb is equal to 0. So this gives us yb is equal to 0 for particular b that we have in the problem. And the second thing that we can see from here is that for now, again using this inequality, if we use this inequality again, then what we can see is that b is equal to 0, then y times any vector in w is positive. So this happens for every vector. So now again you can take the vector to be minus of itself and then can deduce that y is also equal to 0. So it's a bit of lengthy computation, but the logic is that using lambda equal to 0 and mu equal to 0, you can deduce that y is also equal to 0. So the hyperplane vector that separates the two is the 0 vector. But this is contradiction to the fact that we should have a non-zero hyperplane separating vector. So this means that the fact that lambda is equal to 0 is not true. So lambda can only be equal to 1, and this with this we come to the end of the proof. The idea is now lambda is equal to 1. We take z equal to 0, x belonging to k and eta greater than alpha. With this, the inequality that we had, the star inequality, this becomes this. Now what you can see is that phi star y minus a must be belonging to k star. The reasoning is again similar. Suppose phi star minus a, this element s, does not belong to k star. It means that there exists a vector x belonging to k such that this is always less than 0. And then what I can do is I can use the fact that it is always less than equal to 0 to multiply it with a suitable scalar, which is a infinite magnitude scalar, to drive the left hand side to minus infinity and get a pathology. So this means that s, which is phi star minus a, must belong to k star. So we are already seeing that this y is a dual feasible point, And now phi star minus a is k star. Now we can choose x to be equal to 0. And this, with this choice, the inequality here becomes just eta upper bounding yb. But now eta is always greater than alpha, so you can take eta to be such that it is alpha plus 1 over n, and in the limit n tending to infinity it is alpha. So this reasoning will give you alpha is always greater than equal to this yb. So now we can incorporate weak duality to say that yb is always greater than equal to alpha, because the dual value is infimum of yb within the set b. So this is always greater than equal to any yb you put, which is greater than equal to alpha by weak duality. So with this we come to the conclusion that alpha is equal to beta. So this is a lengthy proof, but it is instructive to see how the inequalities play out in this proof. The main idea is that I will repeat the condition of strong duality is given by Slater's theorem, which says that your dual feasible set or primal feasible set should be non-empty, and there should belong the opposite. So there should belong a primal feasible point or a dual feasible point in the relative interior to guarantee alpha is equal to beta. So this relative interior, it plays out important role when we try to separate lambda equal to 0 particularly. So with this I end the video. In the next video we will talk about quantum algorithms. Particularly I will start with Deutsch-Jozsa algorithm, and let's see.